In order to set up a custom estimator using TensorFlow's Estimator API, the model function has to be defined in a very specific way. What are the input arguments to this model function? Now, for our second demo on convolutional neural networks in this course, we'll build the same neural network. That is, we'll use the same architecture, two convolutional layers with a pooling layer at the end. The difference here is that we'll work on a different data set. We'll use MNIST images. You'll see how the accuracy of our same model will increase when we use a simpler data set. Another thing we'll do is we'll package this neural network into a custom estimator. In this course, we've already seen several different examples of built-in estimators: the linear regressor, the linear classifier, the DNN regressor, and the DNN classifier, to name a few. But we haven't really built an estimator using a custom model that we've developed. That's what we are going to do in this lecture. The import statements are pretty much the same as before. In fact, we don't really use NumPy, Pandas, or SciPy in this code. I just leave those imports in there in case I want to manipulate data using those libraries. We'll be classifying images in the MNIST dataset. TensorFlow provides handy library functions which we can use to access the MNIST dataset directly. You don't need to make a URL request to a website and download the gzipped file. TensorFlow libraries abstract all this away from you and provide a nice wrapper allowing you to access MNIST data in batches. Since we're working with images, we'll use the matplotlib library to plot these images to screen. We want the plots to show up inline in our Jupyter notebook, which is why we specify matplotlib inline. In TensorFlow, you can simply call input data.read datasets, and that will load the MNIST data after downloading it onto your local machine. The data is all available for you in the MNIST variable. I'll set up a very similar display underscore digit helper function, which will plot one digit from the MNIST data set to screen. We need to reshape the data before we can plot it in the form of an image. This is because the MNIST data is available in the form of one-dimensional arrays. Every digit, which is 28 by 28, is represented in the form of a one-dimensional array of 784 pixels. We'll reshape it into a 2D image representation and use matplotlib to plot it to screen. We'll quickly test that this display digit helper function works by plotting one of our images from the training dataset. Initialize the images for our convolutional neural network. The one change here is that the height, width, and the number of channels for our image has changed. The MNIST dataset comprises of images which are 28 by 28 pixels. These are grayscale images, which is why the number of channels is equal to 1. The number of neurons in the input layer will be height multiplied by width, that is 784. Here are the parameters for our first convolutional layer. They're exactly the same as our earlier demo. You can, of course, try a different convolutional neural network architecture and see how that works for you. And here are the parameters for our second convolutional layer with 64 feature maps. And finally, our pooling layer, which follows these two convolutional layers. The depth of the pooling layer is the same as the number of feature maps in the last convolutional layer to which it's connected. We have the same fully connected layer with 64 neurons, and the number of outputs is equal to 10. Here, the number of outputs is different from our previous data set where we use the street view housing numbers. That's because the digits in that data set range from 1 to 10. The digits in the MNIST data set range from 0 to 9, which is why we specify 10 as the number of outputs. Because this convolutional neural network is going to be a custom model that we'll call using a custom estimator function, we'll set up a helper function which will allow us to build this neural network. That is our build underscore CNN helper function. The input argument here is the features dictionary, which contains the features for our custom model. And here is our X placeholder. Our X placeholder basically accesses the images key of our features dictionary. We'll pass in the training images as values associated with the images key. We need to reshape the input data because the MNIST images are specified in the form of one dimensional arrays with a length of 784, that is 28 multiplied by 28. However, a convolutional neural network expects the images to be in the form of a four-dimensional image tensor, where the first dimension is the batch size, then height, width, and channels. So we call tf.reshape to reshape the input data in this form. Once we have the training data, we can set up the convolutional layers as before using tf.layers.conv2d. Remember to specify the ReLU activation for our convolutional layer. Set up the second convolution layer which follows the first, once again exactly like before with the ReLU activation function. After the two convolution layers comes the pooling layer with valid padding. That means no zero padding will be applied to the input of the pooling layer. We flatten the pooling layer into one-dimensional data by calling tf.reshape. This is so that the pooling data can be passed into a fully connected dense neural network layer. Remember that we are now working on the MNIST dataset. The size of the images in the MNIST dataset is 28 by 28, and the size of this input image has been reduced 4 times. The image that is the output of our pooling layer is a 7 by 7 image. The parameters to our reshape function will differ slightly because of this. It's 64 multiplied by 7 multiplied by 7. That is the size of our one-dimensional array representing the image output of our pooling layer. Pass this flattened pooling array to our fully connected layer with 64 neurons and ReLU activation, and pass the output of this fully connected layer to our softmax activation layer, that is the logits layer, which we'll apply the softmax cross entropy when we specify our objective function. In order to build a custom estimator using TensorFlow's Estimator API, we need to specify a model function, that is the CNN underscore model underscore function that you see on screen. This model function takes in three arguments: the features, labels, and the mode in which this model operates. This model function will return an estimator spec definition, which will contain the various parameters that our custom estimator needs. An estimator model can work in one of three modes: prediction, evaluation, and training. That's what this input argument specifies. And the estimator spec that we'll build will be different based on the mode in which this custom model operates. Use our helper function build CNN to build our convolutional neural network. The return value from this helper function is the logits layer, and this logits layer that we'll use in our cross entropy objective function. The predicted output of our machine learning model is that digit which has the highest probability value as the output of our softmax activation layer. So we call tf.argmax to get that digit. And really, our convolutional neural network model, along with the predicted classes, is all the information that we need to set up the estimator spec in the predict mode. So, if it's the prediction mode that we are operating in, we simply instantiate a tf.estimator.estimator spec, pass in the mode, and pass in the predicted classes. For the training and evaluation modes, we need to pass more information to the estimator spec, namely the loss function. The loss function is the same as before: tf.reduce mean on sparse softmax cross entropy with logits. Set up the Adam optimizer, once again no change here, and set up a training operation which minimizes our loss. Notice the global step is equal to tf.train.get global step. This is necessary. If you don't specify this, your training will run forever. Our optimizer uses this information to get the number of steps for which it needs to run. If our model is going to be used in training mode, we have enough information to set up the estimator spec, pass in the mode, the loss function, and our training operation. You can't train your machine learning model without a loss function and a training operation. And this is what we need to specify when the mode is set to train. There's one last bit of information that we need to provide to the estimator spec when we run our model in evaluation mode. That is, How will we validate this particular model? We use accuracy and we specify tf.metrics.accuracy for our eval metrics ops. We've spoken about different metrics that we can use to evaluate our machine learning model. Since this is a prototype model, we're just classifying handwritten digits, we can use accuracy. We'll run training on this model for 2000 steps with a batch size of 100. Remember that you can choose to specify either the number of epochs or the number of steps when you use an estimator. Here I've gone with number of steps. Setting up an estimator with a custom model is very simple indeed. You simply instantiate a tf.estimator.estimator and pass in a model function. A model function is our CNN model function. In order to use this estimator, we specify an input function, which here is a simple numpy input function. There is our training data, mnist.train.images, and the corresponding labels, mnist.train.labels. We specify the batch size, set number of epochs to none, since we'll be specifying a number of steps when we actually train our model, and set shuffle is equal to true for the training phase. All that's left to do now is to call model.train and watch the progress. Let's run this model on our test data. We specify another input function for this. It's once again a numpy input function, but this time it takes in test images and test labels. Go ahead and call model.evaluate and pass in the test data. Because we've specified accuracy as one of our metrics when we set up the estimator spec for the evaluation mode, the evaluation result will show us the value of accuracy on our test data. Notice that for the same convolutional neural network, we've achieved an accuracy of 98% on the MNIST dataset. That's because it's a far simpler dataset. The model function takes in three input arguments. The first is the features in the form of a dictionary so that you can specify multiple features in one go. The second is the labels, and the third is the mode in which the estimator is to operate. The mode can be training, prediction, or evaluation mode.